here this is a time scale for the erase and program. Erase like 100 milliseconds, and program can be a little bit faster, like 10 microseconds, and we need to pass large current, like 6 microamp. So then after that, we can do the read operation. So if you want to read, then what do you do here? Any idea? So for the read, the drain, you need to apply some small voltage, like 1 volt, because in this case you don't want to program. Previously, when you program, you apply 5 volts or 6 volts. Now, if you want to just read, then you apply some small voltage, like 1 volt in this case. Still need to fully turn on this transistor by 5 volts to the gate. So here, those voltages are some medium voltages, because you don't want to program, you don't want to have this FN turning or channel holding electron, but you just want to read out the current, so you apply those numbers. And then depending on the threshold voltage here, then this 5 volts may be larger than threshold voltage in the erased state, so you will get the current out. Or maybe in the program state, this 5 volt is less than your threshold voltage, then you don't have the current readout, so you get 0. So this is how you read. So then here is again, you apply the 5 volts to the word line, and then you have 1 volt to the bit line, and this is the selected cell. You only read this cell. And read can be fast, like 50 nanoseconds. So this is for the NOR flash operation.
So for the program, you said you need 2L for the channel length.
Yes.
Yeah. Is it better if you have 1L? You have even more electric field, larger electric
yes.
field. Then you have more electrons going into.
You may break down your device. Yeah. Because 5 volts or 6 volts is very large. So this is the operation principle for the NOR flash. And there are some disturbed issues in the NOR flash array. So this is when you look at this program's case. Cell A is a selected cell. You only want to program cell A, but the other device which share the same word line or the same bit line with cell A will be under this so-called disturbed state. This is because, for example, the cell B here is the same word line as cell A, but you don't want to program cell B. So what you do here is to apply 0 voltage to the cell B's bit line here. So cell A is a program cell, so you apply 6 volts. But cell B, you apply 0 volts there. So although it's 0, but cell B is still, you say, the word line is 12 volts. That means cell B's gate is 12 volts. So this is still kind of large voltage. This 12 volts to the source, which is the ground. You don't have the channel hot electron, but this 12 volts across the gate to source may still have some tunneling to the cell B. So the cell B may be so-called disturbed. That means the threshold voltage of cell B may shift a little bit. So this is so-called the disturbed state. And similarly, cell C may be under the disturb, because cell C share the same bit line as the cell A. So if you want to prevent cell C from being programmed, so you apply 0 to the word line of the cell C. But cell C shares the same bit line as cell A, so that means the cell C's stream voltage is 6 volts. So still cell C may have the current the drain current, especially when the cell C is erased. So by the way, so for the flash transistor, the erased state, typically the VTH is negative voltage. So even cell C, the word line is 0, cell C actually is turned on. So the cell C may be disturbed as well. So those are the program disturb problem for the NOR flash. And we will talk about more of those reliability issues later in more details. Okay, any questions? Then let's move to the NAND. So again, this is a NAND layout, and I want you to correlate this layout, let's say the schematic of this circuit diagram here, to this cross-sectional view of the NAND, and then to the cell layout from the top view here. So the circuit diagram, as we discussed, you will have a multiple wire line control those floating gate transistor, and those floating gate transistor will be in series. And then at the top end, you will select transistor, and bottom end you will have another select transistor. And then the top select transistor connect to the bit NAND, bottom select transistor connect to the common source NAND. So that's the architecture. And then if you look at one string, and then if you lay down that one string horizontally, and if you look at cross section, so this is a cross-sectional view, and this is a string, and then this is the top select, this is the bottom select, this is this select here, and then this select. After that, you connect to the bit NAND. So here you have, after that, you connect to the bit NAND. And this one, after that, you connect to the source NAND. So after that, here you connect to the source NAND. Here the source NAND is in and out of the plane, okay, perpendicular to the bit NAND. Because here you say this is perpendicular. And you ask the question, how many cells in this string, right? So you see here the number, 64. This is a typical number. And the cell layout from the top view, okay. Then if you look at those two cells, so from the top view is something like this. This is the wire line, and this is the bit NAND. So this is the source, gate, and drain. And you see here is 2F by 2F. Why is that? Any idea?
There is no contact.
There's no contact. Yeah, that's a key. Because these transistors, they share the source or drain. This is N plus doping, for example, right? So you don't make contact here. They're in series. Those transistors in series, right? And here you don't make a contact. There's no access to this node, so you don't need the contact. Then those two transistors just share that drain or source. Then you just need to have F in between. So then you only have half F here, and half F here, and then F here. Then you have 2F. So in total you have 4F squared. Of course, this is a rough estimation because at the very end, for the after the select transistor, you still need to make a contact with the top bit NAND. But it's close to 4F squared because every 64 cells you only have that one contact. So if you average that out, then it's very close to 4f squared each cell.
Is there capacitance between the two transistors connected in series in that connection node?
Yeah. Yes.
So
that will cause some problem. We will talk about later. Yeah. Okay. So then let's look at this NAND flash, the organization. And for example, if you have 2 gigabit per chip, so what is typically partition like this. So still you can have 8 bits as 1 byte, and then for 1 page you have this kind of byte. So what does this mean? Again, this page is the same as the DRAM. 1 page means 1 word line. So 1 row, let's say. And then this is number of word line, basically. It's like this 2048, 2000. Of course, if you consider 8 bits, then we multiply by 8. So this will multiply by 8. So that's the number of word line. Then what is the number of the bit line? Oh, sorry, just made a mistake. This is bit line, sorry. Because 1 page is 1 word line, but it determines how many bit lines. Okay. So this is number of bit line, and the number of word line is here, right? So because look at this string, 1 string. You have 64 word lines. So this is number of word line. And if you have those two multiplied together, that is 1 block. Okay. Basically 1 subarray in the NAND flash. And typically people call it block, 1 block. And in this 2 gigabit chip, there are like 2048 blocks. So this is the typical organization. So if you look at the NAND flash, the array is very rectangular. Okay.
All blocks share a common bit line, or they have separate bit lines? Like word lines are.
Word lines are shared across the whole block.
The whole no, but multiple blocks they share one common bit line, or they have their own.
Different blocks are different.
2048 across different bit lines. Okay.
Different bit lines, because after end of this bit line you will have some sum.
Okay.
Yeah. So the it's very rectangular, this one, right? So if this is the array, it's something like this, because here you will have like this 2 kilobytes, or let's say 16 kilo columns, and this side is only like 64. So the NAND flash is very rectangular. It's not like SRAM, you may have 128 by 128. So this one is like 64 by 16,000, something like that. So there's a reason behind this. Okay, so we can talk about that later. But anyone has any idea why it's like this? Why? What limits the number of the cells in one string?
The capacitance between each two.
Maybe we can talk about this later after we talk about the operation principle. So you may have better ideas.
You have to go through each cell, slows down everything.
So let's look at this in more details. So again, this is like the array, right? We talk about very rectangular, so they have many dot here. So in this example, there's only 32 cells, but typically like 64, and even this days like maybe 128 is possible. And the page size is very large, as I said. So 2K actually is a small example. Larger one can be like 16K bytes. Byte means needs to be times 8. So here, this is important. So the read and the program operations are performed per page. Okay. So when you do the read, you're going to read this page. Of course, you don't need to select each column out depending on your marks, but you are going to read this one row, and then you may select some of the cells to be marked out. And the program is also along this page. But when you erase, you have to erase this whole block to the top of the exact bias condition in the next 2 slides. Okay, so let's look at erase first. So as I just said, the erase are performed in the unit of block, like single block or multiple blocks. So it's block based, and it's based on the channel FN terming. So what you want to do here, erase, again, these electrons need to go out. So what you can do is to apply 20 volts to the substrate and ground the gate. So electrons will turn through. That means here, for this string, what you want to do is for all the word lengths, you apply 0 volts. And then the substrate, 20 volts. This is block erase because the substrate is shared across one block. So when you apply 20 volts to the substrate, multiple strings, let's say the whole block, substrate is 20 volts. And this word line is across the whole block. So the whole block will be erased. And typically erase time speed is like a few milliseconds. It's pretty slow. So this is erase. Just one more note here. For the select gate, what do you want to apply? So the select gate, which is at the very top and bottom of the string. What do you want to apply? Here it says floating. F. So remember, this top and bottom select transistor are not floating gate transistor. It's just regular CMOS transistor. It cannot sustain this 20 volts. So 20 volt is only for this floating gate transistor because you have this double 2 gates and a very thick oxide, so you can have 20 volts. For those regular transistors, 20 volt of course will break down. So what you want to do is, if your substrate has 20 volts, this one either you have the same 20 volts or you float, then you don't have the actual voltage across that. And then let's look at the program. It's a bit tricky here. So let's say the program, and let's look at this. So if this one is a selected cell to program, okay, and for the program, what you want to do is to have FN turning again, but this time you want 20 volts to the gate and the ground substrate. So electrons will turn through this way, go into the floating gate. So what you need to do is to apply 20 volts to this word line, to the selected gate or selected cell. And then you want to ground the substrate as the channel of this. You want to ground the channel of this selected cell. So you need to apply 0 volt to the bit NAND. This is word NAND. This is bit NAND. So you need to apply 0 voltage to the bit NAND. However, there's one problem here. This 0 volts needs to be transferred to here, because you apply it from this terminal, but then here we have additional transistors in series. So what you need to do is to open those transistors, make sure this 0 volt can be transferred down to here. To open that transistor, that means you have to, for the first one, this string select, you have to turn it on by some voltage. For example, in this case, 10 volts. And then for the other transistors, we need to apply a voltage called Vm to turn it on. And this Vm voltage choice is tricky. Okay, we will talk about how to choose this voltage later. But you need to turn it on, roughly the same as maybe 9 volts. So if you have 10 volt and 9 volt here, those two transistors are turned on, so this 0 volt can go to here, and then this selected cell can be programmed. Okay. And then we will talk about some very important concept in the NAND flash, which is called Inhibit. So this is for the other cells. For example, the cell A, which is here. So this cell A is a little bit tricky. We need to turn on cell A to pass this 0 voltage down. So we need to turn it on. For example, use this Vm voltage. So Vm voltage needs to be a little bit large, like 9 volts in this case. And this Vm cannot be too large. If Vm is the same as 20 volts, then cell A will be programmed. So this is not what you want. And this figure shows the VTH shift. This is a VTH shift with different Vm voltage for the cell A. So if the Vm voltage is larger, let's say larger than this, like 11 or 12 volts, you will see cell A's VTH is increasing. This means cell A is being programmed or disturbed. This is not what you want. So you have to make sure Vm is smaller than this, like 11 volts. So the Vm needs to be smaller than this value. So this is to inhibit the cell A. But again, for the NAND, the cell B will have some trouble here. As long as the cells share the same word line or share the same bit line, they will have trouble. Cell B shares the same word line as cell A. So that means 20 volts on the gate of cell B. And then if we don't want to program cell B, then what do we do? We need to inhibit cell B. So the only way to inhibit cell B is to raise the potential of the cell B's channel to some medium voltage, for example 9 volts. So we want to apply like 9 volts to the bit line of the cell B. Again, this 9 volts needs to be transferred down to the cell B. So we need to pass this 9 volts. So when you pass this 9 volt here, for example, the first transistor, the top select transistor, gate is 10, and the drain is 9 volts. So this 9 volt can be passed down to here 9 volts. So by the way, here I didn't mention that, but I should mention that the bottom select is 0 volts. So this will make the string floating. So all those two strings will be in the floating because it will not connect to the ground. So it's floating. So a transistor is floating. That means what? The source side is floating. So floating means the voltage is undefined, okay? And this voltage will be determined by gate and the drain. And this voltage actually will be the minimum of the Vg minus Vt and Vd, whichever is smaller. For example, if Vg is very large, so the Vd will be fully transferred to the source. Because there's no current flow, this is floating. So then eventually this will be equal potential. So then the source will be the same as Vd. However, if the Vg is small, the Vd cannot be transferred to the source because Vg will be minus Vt. There is a Vth drop of an NMOS transistor. So if Vg is small, then the source side can only go up to Vg minus Vt. So this is the operation for this transistor, which is source side is floating. So this applies to this string of the NAND flash. So again, here this 9 volt, you need to transfer that. So it will pass the top select 10 volts and the Vm. So this Vm is tricky, okay? So Vm cannot be too small. If Vm is very small, as we discussed here, if Vm is small, so the source side of the Vm, or this transistor, can only be Vm minus Vth. So that means this 9 volt cannot pass to cell B. So we want 9 volt to pass to cell B. The reason is that if the cell B's channel is 9 volts, the cell B's gate to channel will be what? 20 volt minus 9 volt, 11 volt. And you hope that 11 volt will not program cell B because you need 20 volts across the gate to channel to program. So you want that 9 volt to be fully transferred to cell B. However, if the Vm is too small, for example, if you design the Vm, this is cell B. If Vm is less than 5 volts, for example, so Vm is 5 volts, then probably the Vth is some number, maybe 1 volt. Then actually what you can transfer to the cell B is 5 volts minus 1 volt. If Vth is 1 volt, then the cell B can only get 4 volts. Although the bit 9 on the top is 9 volts, that 9 volt cannot be transferred. So what cell B gets is 4 volts to the channel. If it's 4 volts to the channel, then gate to channel is 20 volt minus 4 volts. You get 16 volts across cell B. Then cell B is kind of under this programming condition. So cell B's Vth will increase. That's why you see here if the Vm is too small, cell B will be programmed. Cell B's Vth is increasing. So you look at the cell A and cell B, that determines the window for the Vm you can apply here. Because if Vm is too large, cell A will be programmed. If Vm is too small, cell B will be programmed. So this is tricky.